Question 6 says, how many distinct arrangements of the letters in mini are there? So we'll probably hopefully recognize this as being very similar to that question we just took a look at a little bit ago as motivating our new last counting technique. So we're trying to do arrangements, but the problem is some of these letters are not distinct. Some of them are identical to one another. So if we remember what we needed to do there, we needed to figure out, well, how many total items are there that we're trying to arrange. So we've got MINNIE, so there's 6 total. Then we have to break it down into the different types of things. So there, in this one is M's, there's I's, N's, and E's. We need to know how many of each there are, which we can see there's 1 M, there's 2 I's, there's 2 N's, and 1 E. And we can just double check. Yep, 1 plus 2 plus 2 plus 1 is 6. So that is all of the letters. So then if we remember that formula, it said to take the total number, do that factorial on the top, and then in the bottom, take all of the different types, how many of each type there is, and do all of those factorials. So 1 factorial, 2 factorial, 2 factorial, 1 factorial in the bottom. So then writing this out, we're going to have 6 times 5 times 4 times 3 times 2 times 1 over 1 factorial is just 1, 2 factorial is 2 times 1, another 2 times 1, and then another times 1. So in the top, we've got 6 times 5 times 4 times 3 times 2, and then times 1 for good measure, 720. In the bottom, we've got a bunch of 1s and then 2 times 2, so that would be 4. So then 720 divided by 4 is 180. So only 180 distinct arrangements. Now let's just go ahead right on to question 7. It says I want to make a keychain out of a collection of 3 blue beads, 5 yellow, 2 green. How many distinct patterns can I make with the beads, assuming that I use all of them? So we might have to think about this one a little bit. It's not the distinct letters, but instead now I've got different types of beads, and we're going to assume that I can't tell the different colors of beads apart from each other. So I can't tell the blue beads apart from each other, or the yellow apart, or the green apart. So I'll need to figure out a total. And then maybe with this one, it's actually easier to do the parts first. So the different types that we have here is the different colors. There's blue, there's yellow, and there's green. We had 2 green, 5 yellow, and 3 blue. So if we add all those up, 3 and 5 and 2 makes 10. So a total of 10 beads that we're going to make an arrangement of. Because if we think about it, a distinct pattern is really just a distinct arrangement. So then the total goes on top according to our formula, and we take this factorial, and then we multiply the factorials of all the types on the bottom. So 3 factorial, 5 factorial times 2 factorial. Now we can, with this, do our simplification still. So we could still simplify by canceling out the largest factorial on the bottom. So when I start to write out 10 factorial, I could do 10 times 9 times 8 times 7 times 6 times, notice once I hit a 5, I could just put 5 factorial, because I also have a 5 factorial in the denominator. So then I could cancel those factorials. So then I'm left with 10 times 9 times 8 times 7 times 6 on top, and in the bottom I've got 3 factorial, which is 3 times 2 times 1, times 2 factorial, which is 2 times 1. So if we compute those, 10 times 9 times 8 times 7 times 6 is, let me just check it one more time, sorry. 10 times 9 times 8 times 7 times 6. Oh, good golly. It would help if I could type right. Let's do one more time. 10, 9, 8, 7, 6. Okay. 30,240. And in the bottom, we're going to have 3 times 2 times 1 times 2 times 1, which is 12. So then we have to do the division. 30,240 divided by 12 is 2,520. So again, these last two are practicing that last new technique where we're doing arrangements, where not all of the things we're arranging are distinct. We can't always tell the different types from, or the different objects from one another. We just have to know how many are in each type.